All right, Happy New Year, Happy New Semester. We are starting off with polynomials, targets 1 and 2. So what you'll notice second semester specifically, our first couple targets will always be about like introducing what type of function we're talking about, since it'll be pretty much brand new information, whereas first semester we had a lot of review, especially at the beginning of units. So target 1 is just determining if we have a function that's a polynomial or not. So we're going to talk about some basic characteristics of what we call a polynomial. The great thing about starting with this is we actually already know two types of polynomial functions. We know all about linear functions, and we know all about quadratic functions, which are both types of polynomial functions. Now there is this one key characteristic that you might hear me bring up today, so I want to go ahead and get that definition out there, and it's the largest exponent. So what we're going to notice is polynomials oftentimes have an exponent or maybe several exponents within the equation, and the biggest one, whatever that is called the degree of the polynomial. So if you hear me refer to that, that's what I'm talking about. So when we look for polynomial equations specifically, there are some characteristics that we have to look out for. So the first thing is that exponents must be positive whole numbers. And so kind of off of that, and we haven't really talked about this yet in Algebra 2, but related to that, there's two things. So first of all, um, variables can't be in the denominator. And I know that sounds kind of strange that that's related to the first thing I said, but if you have a variable in the denominator, so in the bottom of a fraction, that actually means you have a negative exponent. And the other thing related to that is that variables, they can't be under a radical. Again, kind of a strange thing to be related to the first statement, but what that means is that your exponent is a fraction, so then we wouldn't have a whole number exponent. And then the other thing that I do want you guys to look out for is absolute value brackets. So this is unrelated, just kind of a separate idea. Variables can't be in absolute value brackets. And we're going to talk about what's bad about absolute value when we get to the graphs. Okay, so let's kind of go through that and knock off some of these equations that we know can't be polynomials based on that. So let's talk about the fact that variables can't be in the denominator. So variables can't be in the denominator, so let's get rid of that one. Variables can't be under a radical, so we would have to get rid of this one. Oh, I missed the first statement. Let me go back to that. It says that exponents must be positive whole numbers. So here we have an exponent that's a 1/3, so we would have to get rid of that. And then also I want to talk about this equation right here, specifically the exponent. So if exponents must be positive whole numbers, what would happen if the exponent or the x value was a 3? Then this exponent would be a negative number. Now it could be positive, but it also could be negative. So because there's that variability, we're going to get rid of it. And then the last thing that we know to be true now is that variables can't be in absolute value brackets, so we're going to get rid of that first equation. So everything remaining is a polynomial, and the one I just circled, that's linear. So I already told you that's a polynomial. This is also linear. This is a quadratic, which is a polynomial, and these remaining two equations are both polynomials as well, and we'll learn more about them. Okay, so now we're talking about graphs. So is the polynomial, or is the graph a polynomial or not? And so what it says here is that they have to have smooth, continuous curves that have a domain of all real numbers. So smooth and continuous are going to be our key things. So smooth means it doesn't come to any sharp points. So if you look at an absolute value graph, it comes to a sharp point. So this is a no. That's not a polynomial. We also know that we can't have absolute value as a polynomial. Here, another sharp point, so that's why this is a no. The second thing that I underlined was that it has to be a continuous curve. And so what continuous looks like is that you can draw the whole graph without picking up your pencil. So if you look at this first graph, if I were to outline it, I would have to pick up my pencil at this point in order to get back up here. So this is a no because it's not continuous. The three remaining graphs all meet the criteria. They are smooth, continuous curves. And if you look at the remaining two here at the bottom, we know that linear functions are polynomials already, and we know that quadratics are polynomials. So we should have been able to identify those right off the bat. All right, so that's target one. That's what a polynomial looks like. And that'll get easier because throughout the entire unit, we'll only be looking at polynomials. So you really have no choice to know what one looks like. Okay, so in target two, we're going to do some operations with polynomials. So we're going to add, subtract, and multiply. So we're going to start with just adding and subtracting, which is really just combining your like terms. So starting off with this first one, I always start with the biggest exponent. I always have, I don't know why. If you look here, the term with the biggest exponent is 3n to the fourth. So we're going to start off with that. And then I'm going to look for anything with n to the third. So I have 1n to the third minus 2n to the third, so that would be negative 1n to the third. And then our constant terms, we have a 2 and a 5, so that would be plus 7. And I actually can't combine this anymore, so my final answer is that. Very colorful. Okay, so the only thing that we have to be really careful of on B is that you are subtracting. So for some of you, it might be helpful if you rewrite this and think about distributing that negative. So write negative 3n squared minus 5. That's a really good strategy that I like to use. But then it's just the same thing. So I'm going to start with my biggest exponent. So negative n to the fourth. And then you guys could probably do this without us showing you. So 5 minus 3n squared, which would be 2n squared. And then our constants, we have 3 minus 5, which is negative 2. We're not going to do anything from there. We're just combining like terms. So it kind of looks like something we might factor, but we're not going to get there quite yet. We will eventually. So again, if you prefer to rewrite when you have a negative, not a bad idea. So I'm just rewriting what was already given. If it's a plus like I'm running across right now, all the signs stay the same. But then here is where I'm going to switch them because I'm going to distribute that negative. You don't have to do that step, just kind of a good strategy. If you try it a couple times and you are making a mistake with the sign, then might be a good idea to go ahead and do that. Okay, so biggest exponent, 5x to the fourth. And then the next biggest exponent I'm seeing is x squared. So I have 7x squared minus 1x squared, which would be 6x squared. And then plus 7x squared, so that was, I already lost count, that's 13x squared. And then I have some x terms. So we have 4x minus 8x, so that would be negative 4, minus 4, which would be negative 8x. And that's my final answer. I can't combine those terms from there. Last one with adding and subtracting. So again, just practicing that rewriting. I have lots of negatives in this problem. That's a third. Okay. Distributing the negative here. And here. Okay, and then combining like terms. So biggest exponent, negative k to the fourth. And then looking for things that are to the third power. So 4 minus 1 is 3, minus another one is 2. And then I have some terms that are just with a k. So 8k plus another 8k would be 16k. And then I have that negative 4 that I'm just going to bring down. All right, so that's adding and subtracting polynomials. And now we're going to get into multiplying polynomials. So on A, we have 2 terms times 2 terms. And so what you can do, you've probably heard this before, the term FOIL. So you can actually FOIL these 2 terms together. Let me go ahead and write this out. So what FOIL stands for is first, outer, inner, and last. So it gives you, it's just a way to kind of organize your distribution. So F is first, so you're going to multiply your first 2 terms together. So that would give me 8r squared. O stands for outer, so go to your outer 2 terms, the ones that are furthest away, and so that would be 4r. I stands for inner, so it's the 2 terms that are closest to each other, which would be negative 32r. And then the last 2 terms, the 2 last terms in the parentheses would be negative 16. And then we kind of hop back where we started at the last half of this target, where we have to combine like terms. So notice that the 2 middle terms are both r. So if I combine those, I get a negative 28r. So that would be my final answer right here. So that FOIL trick only works when you are distributing 2 to 2. So it's like a 2 times 2 situation. So on B, C, and D, we can't use that. It'll mess us up in our process. So what I like to do when it's not a FOIL situation is I take this first value in the first set of parentheses and I multiply it times everything in the second set. Notice I'm not actually multiplying right now. I'm just writing out what that multiplication would look like. And then I take the second number in parentheses and I do the same thing. Then I'm going to have to multiply that by everything in the second set. So it's like a double distribution, but this is just kind of a way to organize your work. Okay, so then I'm going to actually distribute. So that would be 5, nope, that would be 40, a to the third plus 5a squared minus 5a. And now I just want to show you another strategy that you can use. When I go into this second distribution with the 6, the first distribution is 6 times 8a squared, which would be 48a squared. And I'm going to actually write that right here, so it's stacked right below the previous a squared term. And then 6 times a is 6a, and 6 times negative 1 is negative 6. Now, you do not have to do this step. The reason that I like it is because then when I go to combine my terms, they're all lined up. So I can see there's just 40a squared, or a to the third. And then for a squared, I have 5 plus 48, which is 53. And then for a, I have negative 5 plus 6, so just 1a minus 6. And it just looks really easy to me when it's lined up that way. You absolutely do not have to organize your work that way. Just giving you a strategy. It might be something that you want to try once and then decide if it works for you or not. On these last 2, it's going to be a very similar process that I just did on B, except that there's 3 terms times 3 terms. So it's going to be a little bit longer. Starting with this 3x squared, I'm going to distribute that first to these 3 terms. So 3x squared, and that's going to be multiplied times x squared plus 4x plus 1. And Then I'm going to do the negative x, so minus x times everything here, so x squared plus 4x plus 1. And then the 2 times everything here. And now I'm going to go through and actually do that. It's a triple distribution this time. And I'm going to organize it the same way I showed you last time, simply because that's actually how I do this. So distributing the 3x squared, that would be 3x to the 4th plus 12x to the 3rd plus 3x squared. So that's the first distribution. Now moving on to the second, where I distribute a negative x. The first term would be a negative x to the 3rd, so I stacked it under my previous x to the 3rd, minus 4x squared minus x, and then I would have 2x squared. 2x squared plus 8x plus 2. And then I'm going to combine all of these, so it's like one big addition problem here. So adding down, so I have a 3x to the 4th, then that would be 11x to the 3rd, and then that would be just a 1x squared plus 7x plus 2. And that's my final answer. It's just so nice because it just organizes it all right for you. Okay, last problem, same idea, different numbers. Starting with 2v squared. I'm just starting down here so I have more room. I think I might want to scooch that over a little bit. Okay, 2v squared times 4v squared plus 6v minus 8. Then I have a negative 7v. And then that 4 times all this. Hopefully you guys are seeing where these numbers are coming from now. Okay. So distributing the 2v squared, so that would be 8v to the 4th plus 12v squared minus 16, oops, sorry, that's v to the 3rd, minus 16v squared. So that's the first distribution. Now the second one, so that would be a negative 28v to the 3rd, then the negative 42v squared plus 56v. And then the last one, starting with a 16v squared, and then that would be 24v minus 32. And again, now I'm just going to add up all these like terms that are already stacked up for me. So I have 8v squared, and then that would be negative 16v to the 3rd, and then this would be negative 42v squared, and then this is going to be 80v minus 32. And there's my final answer. And that, my friends, is targets 1 and 2.